you, Jeremy. So, what I'm going to talk about is information entropy in the classical ideal gas, and I'm going to expand on some of those points that Jeremy made in a little bit more detail, because I have been concerned about entropy for some considerable time, ever since I realised that I didn't understand it. And I came to the conclusion that I didn't understand it because the concept was fundamentally flawed. You know, there are some things I don't understand because they're too complicated. String theory is one. I don't understand string theory, but I'm not going to criticise string theory because I don't know anything about it. But entropy, no matter which way I looked at it, I found a contradiction. Look at it this way, you understand one thing, you look at it that way, doesn't agree with it. I thought, there's got to be something wrong. And a few years ago, I was at a conference in Berlin, and somebody stood up and gave a quotation by Sommerfeld, and he said, thermodynamics is a funny subject. The first time you meet it, you don't understand anything. The second time you meet it, you think you understand it apart from one or two little bits. But the third time you meet it, you know you don't understand it, but by then you're so familiar with it, it doesn't matter. And I thought that was quite witty, but then I thought, actually what Sommerfeld is saying is thermodynamics is impossible to understand. And if that's the case, then there's got to be something wrong with it. And so, you know, I've been focusing on entropy for quite some time. And, you know, looking at statistical mechanics as well as the foundations of entropy. So for the first part of what I'm going to talk about, I'm going to talk a little bit about the historical foundations of entropy, because I think that's where it goes wrong. I cannot, in a short talk, convey the complexity of my arguments because they are quite complex. But I've gone into them in length in the paper that will be published in the proceedings, and so I'll refer you there. But I will draw out some of the salient points. And then I'm going to look more closely at that link between statistical mechanics and thermodynamics. And in particular, I'm going to address that, you know, this particular thing. What is information entropy? In the context of a classical ideal gas, because that's easy to simulate, and everything in thermodynamics should refer to this concept. If it doesn't, then you have a problem. So, what I'm going to talk about in this talk is basically a few things. I mentioned reversibility, Jeremy's touched on it, so I might brush over some of these things. Entropy, I'm going to then look at, you know, the microscopic view. You know, I'm going to mention Maxwell. I mentioned the statistical mechanics of Gibbs, because I think there are some problems there. And I'm going to ask in particular, is it a physical theory? And then look at information theory. One of the problems you have with both statistical mechanics and thermodynamics is that it works. You know, you can use it, you can make calculations, you can make quite complicated calculations, and you get seemingly sensible results. And so when you come along and say, I don't agree with the foundations, people say, no, that's fine, no problem. What does it matter? Because it works. But if it's not correct, then we should be concerned. You know, because one of the subtexts of this symposium is the search for truth. And you know, I have to think truth is quite important. So what I'm going to look at are the foundations first. Now, you know, I'll draw attention to some key moments. Obviously, it started with Carnot, his article on the motive power of heat in 1824, which almost slipped into obscurity, but it was rescued by Clausius, who published, among a number of papers, 4 important papers on thermodynamics. The first one was called On the Moving Force of Heat in 1850, where he reworked Carnot's theory and made the important change. Carnot believed in heat as a material substance, caloric. Clausius dispensed with that idea and introduced the dynamical theory of heat, you know, the idea that heat is motion. 1854, he published on a modified form the second fundamental theorem, the second fundamental theorem being now what we understand as the second law. 1862, just 12 years after this paper, the extension of the second fundamental theorem, and that's where Clausius put forward his inequality, the idea that entropy increases, although it's not explicitly stated in that paper. And it was 1865 when he summarised some of his results, convenient forms of the fundamental equations, and that's where, if my memory serves me correct, he expressed the view that the entropy of the universe always increases. And if we look at what Klaus has said on reversibility, I'm not going to touch on any more modern version, but it's important to understand what Klaus has said. You know, different kinds of operations, as far as external appearances are concerned, are rather numerous. He mentions the transmission of heat by mere conduction. He goes on to say in the same passage, other cases are the production of heat by friction, together, and I put this in italics, together with all cases where a force in doing mechanical work has not to overcome unequal resistance and therefore produces a perceptible external motion, more or less velocity, with this lever of which after we pass it into heat, and we get the same idea, is that if you've got anything happening which produces perceptible external motion, then it's irreversible. And the perceptible external motion is not necessarily the motion of a piston. You mentioned the free expansion of a gas as an example in which that occurred on the graph. So he was talking about large-scale hydrodynamic motion, and he was talking about this Weber of which afterwards passes into heat. And this is where Klaus gets really, really confusing for the modern reader. I have been reading Klaus's papers, those 4 papers, especially the first 3. I have read them, and read them, reread them, again and again and again. And every time I read them, I read something new into it, because it took me years to understand it. You cannot understand Klaus's unless you understand this particular conception of heat. He might have actually dispensed with caloric, but he didn't have a modern theory of heat. His idea of heat was essentially that it was kinetic energy. And so he talked about heat as if it was a property of a body. This jug of water has got so much heat. You know, thermodynamics has dispensed with that view for quite some time. But Klaus's whole thinking about heat, about entropy, about thermodynamics is based on that condition. And what I'll attempt to show is that it's a logical idea in Klaus's. If this contains so much heat, and I change that heat, there's got to be an entropy associated with it. But these days, we think of heat as an exchange. It's an interaction. Heat flows into it or out of it. It becomes energy. Well, it's a form of energy. But we don't necessarily associate the entropy with the change. We associate the entropy with some property of the body. Klaus associated the entropy with the property of the body because he believed that heat was a property of the body. And so when he talks about this Weber of which passing into heat, the kinetic energy of large-scale motions becoming the microscopic kinetic energy of the particles. So you can read Klaus in a modern way, you just end up getting confused. Now Sommerfeld, the man who couldn't understand thermodynamics, although he wrote a book on it, which I found quite useful at times, he conceived of a quasi-static process is at the bottom, take the waves off microscope, and the thing back up. But what you realise, of course, is that that is actually not reversible. We put a number of ideas on reversibility. One of them is that if you perform the process in reverse, you'll leave everything unchanged. And you'll realise, of course, that if you go through this process, in order to come back, you've got to take the first weight off. And so the net effect of a series of these processes is to transform a weight from there to the bottom. And if you repeat the cycle, you'll do it again and again and again, and you'll end up with a load of matter at the bottom. So it's not actually reversible. You know, and you can express that mathematically. You know, it's just the sum of terms, the work done in the forward direction, weight times y1 plus 2w times y2, but now you've got 2 weights, then you've got 3 weights, etc. And then you've got this series. And the work done in the reverse process is essentially the same series, but without this last step, because that's not there. You know, you've got to get question is, the reversibility paradox. It is not possible to make such a process truly reversible without reducing W to 0. But then, no work can be done at all. So, is it reversible? Some of it was quite clear, that we can just ignore the bits at the end. It's approximately reversible. So are we justified in ignoring that dissipation? Possibly. If the dissipative mechanism is extrinsic. So if you have a classical ideal gas, and you can say that we can integrate the work done from A to B, and the work done is P dV, then if I perform the work in the opposite direction, then I just get the negative amount of work. But you need some sort of mechanism of dissipation, because it's a bit like a spring. If you just put that weight on there, it's going to oscillate, even very small. So in order to get it to go to rest, you need some sort of dissipation. And so if the dissipation mechanism is extrinsic, say friction, you can separate out the work done against the friction and the work done in the gas. And then you could possibly extrapolate to say that yes, this is a reversible process. On the other hand, you cannot ignore it, no, if the dissipating mechanism is intrinsic. This is what I was talking about 2 years ago. My simulations on work done in the classical ideal gas suggested to me that actually this focus on quasi-static processes had obscured a simple mechanism of dissipation in a classical ideal gas, because when you have a piston moving in one dimension and the gas particles interact with that piston, if you're assuming some an elastic collision, then momentum is changed in one direction only. And so if you don't do anything, the momentum in the direction of the motion of the piston within the gas is different from the momentum in the orthogonal directions. And of course what happens is you get into particle collisions that leads to an equipartition of energy. And that mechanism is dissipated. And if it is dissipated, what you find, especially for a small change in volume, is that the work done is not PdV, but it's the pressure, the final pressure, the pressure of B times delta V. And that's not the same as the work done in the reverse direction, because now the work done in the reverse direction is the final pressure, which is the pressure at A times delta V. And that mechanism is entirely intrinsic, so it doesn't matter how far, how much you reduce that weight. There's an inbuilt intrinsic irreversibility into that process. So it's not a truly reversible process. And then that then leads to the conclusion, or leads to the question, if you're basing your whole idea of entropy on this quasi-static process, and that quasi-static process is fundamentally irreversible, if you're looking at the flow of heat, as Jeremy has mentioned, into the system and then out of the system, and that's fundamentally different, even just like a tiny, tiny amount, can you really say that it's a state function? I don't know. But that's, Clausius went on from there. Clausius's early work, especially in that 1850 paper, was concerned with the Carnot cycle. But right from the outset, Clausius was interested in what he called internal work, and that is the work that's done in overcoming interparticle forces. And for someone like Kelvin or Thomson and Clausius, not Clausius, Carnot, that was irrelevant, because for them, the cycle was all important. And Thomson states quite explicitly in his papers, what happens to the working fluid is irrelevant because you go back to the original state. But Clausius was interested in what he called internal work. And so he sought to extend the theory of cyclic processes, and this is the crucial thing. This hasn't been realised yet. I'm tempted to publish this paper, but I tried the History of Science journal. I'm not a historian of science, and so I got the style wrong. But the referee did point out that this was actually an important insight that Clausius had sought. He just basically took the results of cycles and said, let's extend that to non-cyclic processes. Because only in non-cyclic processes that you see this in internal work. You know, if you go back to the same state, the gas is at the same state, you don't see any effect of the internal work. And so what he actively looked for was an equivalent equation to that. That was the central result of his work on cyclic processes. You'll notice that the sign is not as you would expect it. You would expect the delta Q upon T to be less than or equal to 0, because in an irreversible process you have to take heat out of the system in order to get back to the same state. Clausius used this sign convention because this function here was what he called his equivalence worth, or equivalence value, and it was based on his peculiar notion of heat. It was based on the idea, it was some property of the body that was manifested by some sort of mysterious transformation of heat into work. But notwithstanding the change of sign, that's what he said. Delta Q upon T around closed irreversible cycles is greater than 0. And it's based on his idea of heat being a property of the body. And what he did was he invented the concept of disgregation, Z, where T dz is greater than or equal to dW. And disgregation really, in essence, describes the separation between the particles. And when he said that this disgregation quantity is always greater, algebraically greater than the work, because in an irreversible process, it's equal if the work done is reversibly different. But then, he did something a bit more to, just to continue with disgregation. Disgregation measures the force of the heat, and this is, again, referring to Clausius's outmoded concept. You might think the force of the heat is just equivalent to pressure, but then you would misunderstand Clausius. In order to determine the force of the heat, we must evidently not consider the resistance which is actually overcome, that's the work that you do, but that which can be overcome. That's in his 1862 paper where he seeks to extend this principle. So, the law does not speak of the work which the heat actually does, but that which it can do. I think these might be my italics, there might be things like that. Similarly, in the first form of the law, it is not of the resistances which the heat overcomes, that's the external pressure, but those which it can overcome that mention is made. And so, Clausius is talking about potentialities. And when he inserted the disgregation into the first law, changed the sign of the Q, which I think is a deliberate change of sign, to derive this inequality. And this inequality, this quantity dz, measures the force of the heat. He's got this inequality here because what he wants to do is measure the work that a gas could do, not what it's actually done. So he's inserted this quantity into the first law of thermodynamics and come up with an inequality. And I suggest to you that that's not something that would actually be accepted in a peer-reviewed journal these days. And he called that quantity there the entropy of the body. So we have the S is greater than or equal to the Q upon T, and that's due to Clausius. And that inequality expresses the fact that in any change in arrangement of the particles, you could do more work than is actually done, and so therefore the entropy will change by more than the amount of heat that flows into the system. But you ask what the equality, what does it really mean? As Jeremy said, Jeremy's a mathematician, and mathematicians like to think with mathematical symbols. If entropy is greater than dq upon T, you can write Tds is greater than or equal to dq plus some quantity d phi. And d phi has to have the units of energy, but dq is defined by the first law of thermodynamics. So what is d phi? D phi lies outside the first law of thermodynamics. It has a unit of energy, but it's not du, dq, dw, or any combination of them. So when people talk about this inequality that entropy can only increase, what they're actually talking about, potentially, and I've never ever seen this discussed in the open literature, but it really, really bothers me. This is a potential violation. Well, it is a violation of conservation of energy. what it's actually saying is that some property of a body with the unit of energy is increasing in a way that lies outside the first law of thermodynamics. I don't know, maybe it's dark energy, but it's something. But I'm deeply skeptical about it. And just to finish off with Clausius, he applied the concept of disgregation to the ideal gas, but there are no interparticle forces, so therefore there's no internal work, and therefore there's no reason to apply the disgregation to the ideal gas. So, you know, he developed this whole theory, then applied it to the ideal gas, and well, it doesn't apply at all. So, yeah, he said PdZ is equal to PdV, PW is equal to Q is equal to 0, Ds is equal to Z, which is greater than 0, and as I said, some property of the gas, the unit of energy is changing. But this PDV is a fictitious workforce, it's the work that could be done in a quasi-static ideal process. It's not what actually done in expansion. So, and it has its origins in measuring the force of the heat. So I asked the question, is it real or not? Well, you probably know my view. So, then we come to the microscopic view. You know, and the emphasis in thermodynamics shifted away from engines and cyclic processes to the microscopic. And if I quote Maxwell in Takes Thermodynamics 1878, if we define thermodynamics as I think we may now do, as the investigation of the dynamical and thermal properties of the bodies, all speculation as to how much energy in a body is in the form of heat, I point out in place, that's aimed directly at Clausius. But Maxwell ultimately adopted Clausius' definition of entropy, even though he rejected his thinking on heat, he nonetheless accepted his definition of entropy. But the significant thing about that is that thermodynamics moved completely away from its origins in cyclic processes to the investigation of thermodynamic phenomena. And Boltzmann's H theorem, was a significant development in statistical thermodynamics. And Boltzmann defined this function H, which is the sum of all of the probability multiplied by the log of the probability. And that's what later Shannon derived the same function, which he called the entropy on the advice of von Neumann. And if we say that S is equal to minus the Boltzmann's constant time H, then what we end up with is this expression S equals 3 over 2 NPT LNT plus NK LNT plus some constant terms. And that agrees with the changes in thermodynamics that we derive quasi-static processes in thermodynamics. And so, Boltzmann saw his H theorem as a microscopic proof of the so-called second law. And I say the so-called second law, and because what he meant by it is that entropy increases in an adiabatic, irreversible process. And, because Boltzmann started with an arbitrary distribution of velocities and let the system evolve, but that's not the same sort of process that Clausius had in mind. And of course, Boltzmann's H theorem was subject to a number of objections at the time from Loesch and Zermelo, both of which are valid as far as I can see. But Boltzmann's work was really concerned with microscopic properties based on the physics of what's actually happening. And gives statistics.
We've only got 5 minutes. We want 10 minutes of questions. No, that's not easy. 12:50 was the mission. 12:50? Yeah, 12:50.
Oh, sorry.
Yeah. Oh, you're okay.
That's good.
But you need time to questions.
I'll leave time for questions.
Right.
I've obviously missed time. I blame Jeremy. So, Gibbs presented the canonical ensemble in 1902, but it wasn't intended to represent physical systems. I'll just read you that. I found it convenient, instead of considering one system of material particles, to consider a large number of systems similar to each other in all respects, except in the initial circumstances of motion, which I suppose would vary from system to system. The total energy being the same in all, that's not quite true of the canonical distribution. But in the statistical investigation of the motion, we confine our attention to the number of these systems which at a given time are in a phase such that the variables which define it lie within given limits. Apart from that bit about the energy being the same, it's actually been almost perfect description of the canonical ensemble, except it wasn't made by Gibbs, it was made by so I suspect that Gibbs just pinched that idea from Maxwell, and that based his idea of the canonical ensemble on that. And it's not intended to represent a physical system. You know, it's a deliberate way of move away from a single system to a collection of systems. And so it's often, but it is often given a physical interpretation. And here's one of the real problems with the canonical ensemble, and one of the problems with entropy. It's often given the interpretation that it represents the probability of finding a small system in contact with a reservoir at a given energy state. And in order to derive it, you take this expression for the entropy, where that is the density of states of the reservoir, ES is the energy of the system. So you express the entropy of the system, you form a Taylor expansion around an energy fluctuation. You say, no, okay, there's fluctuations, there's an exchange of energy between the system and the reservoir. If I form a Taylor expansion, you do various bits of manipulation. You put that equal to that, which in itself is dubious because that's a fluctuation, it's not heat. But you then end up with this expression for the canonical distribution, which is well known, leads to very sensible results on whatever. But if you calculate the information entropy, which I then talked about, what you end up with is this, that the entropy depends on the Boltzmann constant, the partition function, the average energy, and the temperature. And none of those fluctuate. And yet the whole essence of deriving this is let's consider a fluctuation and do a Taylor expansion. So that's nonsense. Yeah, I suggest. And similar considerations apply to the grand canonical distribution. It's often derived in terms of particle number. Use that as your basic distribution, but now you've got this term un for the particles in there. And again, you get similar expression. You've got K, Z, the energy averaged over particle number and energy, T, and mu and N. All average quantities, none of which fluctuate. So there's a real problem there with statistical mechanical interpretation of entropy. But in the 1950s, James and Trebus in the 1960s then made this link between thermodynamics and information theory. And James published 2 papers on the subject, and he essentially said that statistical mechanics was not a physical theory. He went further and claimed that it need not be, because the techniques of statistical inference allow physically useful properties of the systems, such as mean energy, mean square deviation, to be derived. So that explains why it's useful. But is that true of entropy? I'm not sure that it is. My feeling is that statistical mechanics was developed to agree with thermodynamics. But if the increase in thermodynamic entropy in an irreversible adiabatic process has no physical basis in energy, which I've already demonstrated earlier, what does this mean for the statistical entropy? In particular, the canonical distribution is not a physical distribution. It doesn't describe a physical system. So if we look at physically descriptive distributions and the energy entropy is different from that of statistical mechanics, what does that mean? That's my fundamental question. So Gibbs said a small part of a larger system is canonically distributed, which means that you can describe the probability that the system occupies a given element of phase as just a product of single particle Maxwellian velocity distribution. That's the system probability, those are single particle Maxwellians. And that leads directly to the gamma distribution. The gamma distribution is just a transformation of that probability distribution. Now the gamma distribution, this echoes what Jeremy said. The statistical mechanics was developed independently of statistics. This is a well-known, well-defined probability distribution. And when I derived it from that, I thought, I've not seen that in any textbook anywhere, so I'll write it up and I'll try to publish it. But the referee said, no, it was derived by Jeans in 1921. In fact, you can trace it back to 1916. And it was given by Kinchin in 1949. Which may be perfectly true, but it just goes to emphasize the point that these two people have dealt with it, but you won't find it in any book on statistical mechanics, or very few. Here, Binter is 1 over kT, gamma is 3n over 2, energy number of particles. And if I reduce that to, if I normalise that energy to temperature 1 over kT, then you can transform that, that's the gamma distribution, and that's the gamma distribution. And if you plot it out, the probability, if you plot this function out here, for 30 particles, 50 particles, 70 particles, 100 particles, you can see that this is almost symmetric. It's almost Gaussian. And in fact, in the limit of a large number of particles, it is Gaussian. And so if you compare that with that, you see that there's a big difference, because the most probable energy state of that is at the mean energy. It's 3n over 2, whereas the most probable energy state of that is 0. So that's another problem of casting a physical interpretation of the canonical distribution. So in order to demonstrate these things, what I've done is I've done some computer simulations of a hard-sphere fluid. You just let them move, and when they approach closer than 2 radii, you let them collide according to the laws of mechanics. And what I've done is I've sampled the energy. And if I sample one particle among 400, I get these histograms. That solid line is the gamma distribution of the single particle. For 3 particles, likewise I get these histograms. That's the gamma distribution, 5 particles. So what that simulation shows is that, the gamma distribution actually does physically describe a collection of hard spheres moving independently and colliding. It describes the accessible energy states. And if I extend it to open systems and I insert a permeable partition, which I did by just inserting fixed spheres, dividing the chamber, so not making particles collide off it. Some of them go through, some of them don't. I just concentrate on one side of it. Then I've got the same sort of system. I've got 400 particles, but I look at a fixed number of them, and I look at how many of those particles appear in the other side. So that's defined by my small system occupancy. This is the binomial distribution, this right here, and these are the actual histograms. And so you can see the occupancy is given by the binomial distribution, which is what you would expect for occupancy. And then if I look at those occupancies and I say, okay, if I take all the instances where I've got, say, 7 particles, 10 particles, 13 particles, and I look at the distribution of energy states, what does it look like? Well, it looks like a gamma distribution. It's noisier because I took 200,000 samples, but that's 200,000 samples of everything. There's not 200,000 samples of the energy states corresponding to 13 particles or 10 particles or 7 particles, but it's just a gamma distribution. So my grand canonical distribution weights some of the what's that there? We'll come on to the grand canonical. I'll just get ahead there. If I want to find the probability that the system is in a given energy state for these open systems, it's just a weighted sum of gamma distributions. If I take a given occupancy, it's got a gamma distribution. And if I want to take the probability of finding the system in a given energy state, it's just a weighted sum of those probabilities. So those are the histograms, that's what I actually find, and that's the weighted sum. So, that's actually a descriptive statistic of the classical ideal gas. The probability of an energy state is given by the gamma distribution for an open system by a weighted sum of gamma distributions, where the weighting factor is the binomial probability. If I want to extend it then to a grand canonical distribution, all I've got to do is I just have a little system and a very large system. And these are the total number of particles. This is the actual occupancy of the small system. Because now if I've got a small system and a very large system, the number of particles that appear on one side of this chamber represents just a small fraction of the other parts. So it should be canonically distributed. So the large system acts as both a thermal reservoir and a particle reservoir. So I can describe the occupancy very simply by the Poisson distribution. That's the Poisson distribution, which is what you'd expect for a very small probability. I've got a ratio of volume there 24 to 1. It's harder to simulate much more than that because it gets a bit tricky. And you've got very, very long distances involved. and I've got these total number of particles. So that's the occupancy of the small system. And then, again, if I look at the energy states, it's just a weighted sum of the gamma distributions. You know, the mean number of particles here, the probability is about 104, something like that. So that would be 4 particles in there, 12, etc., etc. It's just a weighted sum of gamma distributions. So what I've got there is a descriptive set of statistics. And so, you know, there are 3 questions. Does entropy fluctuate with energy? You know, the whole purpose of looking at this is to say, you know, you can derive the entropy of or derive the canonical distribution with regard to entropy fluctuations. So does it fluctuate? Should it fluctuate? Which is the more fundamental variable, energy or phase, but velocity in my case, and what is the entropy in an open system? So if we look at fluctuations in energy, entropy, in information theory, entropy represents uncertainty. It represents the total number of possibilities that might occur in a single measurement of a system where you've got a probability distribution. So to say that it fluctuates with a given instance of that probability distribution has no meaning. It represents uncertainty. So it should not fluctuate. And the single particle gamma distribution shows that the velocity of a single particle is always governed by the Maxwellian. You know, the fact that you can take this single particle and trace it through time and it obeys a gamma distribution, which is just a transformation of the Maxwellian velocity, means that it's always given by the Maxwellian velocity distribution. So if I take a system, for example, with 300 particles, and I look at the distribution of velocities across it, it's recognizably Maxwell-Boltzmann speed distribution, but it's not exact. And if I look at the entropy, the H function calculated from the exact distribution of the particles, it fluctuates. But what I've got there, you know, having said that entropy doesn't fluctuate, what I've got there is I've got 2 ways of calculating entropy. I can either take this as my probability, these histograms, or I can take this as my probability, this limiting distribution. If I take the histograms, then it fluctuates. And if I increase the number of particles, the mean H function comes out to some value, and the standard deviation fluctuates, and that's Boltzmann's H theorem. So when Boltzmann said the system evolves and the entropy increases, what he was actually saying is, if you take the entropy as that distribution, that fraction of particle that's in a given state, then the entropy increases. But in fact, the entropy doesn't increase, because the system is always Maxwellian. And what Boltzmann showed was, he basically showed that, where he didn't interpret that way. So entropy doesn't fluctuate, not in information theory. Which variable? If I take that probability distribution there, and I calculate the entropy for it, that's what I get. And this is independent of temperature, that H function, because this is energy over kT. So that clearly doesn't have any thermodynamic significance. If I transform to energy itself, then the energy dependence is given by this term, 1 over kT. Sorry, the temperature dependence. So that doesn't agree with thermodynamics. But if I take this probability of this phase probability, single particle Maxwellian distribution, then I get this. So that tells us that energy is not actually a good basis for entropy. So the canonical distribution of Gibbs, which tells you that really it doesn't matter whether you take energy or velocity, it's not valid when you consider a physically descriptive distribution of systems. Energy as a basis for probability just doesn't work. It's got to be a distribution of the velocities. And that's what we find. So only the latter agrees with thermodynamics. Because that's what you get from thermodynamics with a so-called quasi-static process. But of course, that problem with phase, I just gave the bit of the velocity there. But you've got this problem with velocity, and the Gibbs paradox says that, you know, if I have 2 equal volumes and I've got an entropy in each. If I double the size, then the entropy should just double. But according to statistical mechanics, because I've got this absolute dependence on volume, I get this extra term here. Whereas thermodynamics would tell me that I just get this term here. So that's the famous Gibbs paradox. So, although you can actually take this distribution over phase, and you can get this distribution, this entropy for it, it doesn't actually agree with thermodynamics. And this is well known. This idea has been around for well over 100 years, and people are still writing papers on it. So there's nothing new there. But if you look at entropy in open systems, and I shall be finishing very shortly, then you find this in Kinch's little book on information theory, that there is this contribution to the entropy. If you've got this joint probability, you get this contribution to the entropy from this. And this is just a weighted average over all the particle numbers. So, what you should end up with is an entropy which depends on the average number of particles, plus this term. So, if I take an open system, in other words, I've still got well-defined volumes, but I've got an uncertainty in the particle number, I get a term in the information entropy. And I suggest that that's non-thermodynamic. There's no thermodynamic counterpart to that entropy. And if that's passed on to Gaussian, you can show that then becomes roughly that. So you get an increase in entropy depending on log n bar, the average number of particles. So that's clearly non-thermodynamic, but what about the term volume? Planck corrected for overcounting by dividing the partition function by n's factorial. That's well known. It says the particles are indistinguishable, so the number of states is far too high. But actually information doesn't deal with states, doesn't deal with the number of states, it deals with probability, and those probability distributions are normalized. That's normalized. That's a proper probability distribution. And so what I find in information theory is that if I have that, and I move to that, I remove the constraint, the entropy increases. And then if I remove that partition, that permeable partition, so I get a completely open volume, well, that entropy increases. That's entirely consistent with information theory. Remove the constraints, the entropy increases. But it's not consistent with thermodynamics. And so what I'd suggest to you is that there are serious doubts over the concept of the entropy of a body as derived by Clausius. It depended on the now defunct idea of the heat of a body and the force of the heat. It gives statistical mechanics is not a physical theory, and attempts to relate it to physical phenomena through entropy fluctuations are flawed. And the physically representative theories of probability in classical ideal gas can be demonstrated through computer models. We need to differentiate between entropy and phase. But here's the crucial thing. Information entropy contains non-thermodynamic components, Hn and possibly Hb. I would suggest that Hb may well be non-thermodynamic. And that then leads to that final conclusion that thermodynamic and information entropies would appear to be different if we use physically descriptive statistics rather than statistics of classical statistical mechanics. And so there are numerous implications, and this is my last slide. For example, there's no Gibbs-Dewey relation if entropy is a function of state. Things like free energy and whatever you thought. Black hole entropy. If there's no entropy of a body, is there such a thing as the entropy of a black hole? I'm not a cosmologist. I leave that to you. Landau's principle, is it valid? Is it what Jeremy started on? Is the information entropy destroyed by reading or writing? In other words, if I've got a two-state system, the only time I have information entropy associated with that two-state system is if I don't know which state it's in. And as a system, as a memory, that's not really very much use. But I find, if I read it and I find out which state it's in, that destroys the information entropy. But is that a thermodynamic process? And so the relationship, the question that Jeremy asked, about which I'm not going to answer, what is the relationship between thermodynamics and information entropy? I'm going to leave it there. Thank you very much.
I think we're a little over time, aren't we?
No, we're not.
I thought it was 20 minutes.
No, we finish at 10 to.
Oh, okay.
We come back at 22. We've got 50 minutes.
All right.
So we've got 5 minutes for questions.
5 minutes for a question. I'll direct them to Jeremy.
Yes, please.
All this is based on it being elastic collisions.
Yes.
What if they're not elastic? Or not linear?
I haven't.
Elastic, you get really...
Yeah, I haven't looked at that because I've restricted everything to the classical ideal gas. That's, if you like, the next phase of my work. I don't know. I will find out. I will do the simulations and find out.
It might be there at the front rather than at the back end.
Yeah. But you know what I talked about there is the classical theory of the classical ideal gas. You know, so
Sorry, I think we should actually... I am actually wrong about this.
right.
We should have finished 5 minutes ago.
I've never heard of that happening before. A couple of quick things. Mike Lawrence has put some takeaway pen drives